Thank you. So, what I'm going to talk today is more about operational resiliency and especially in the control room and what can be done. And there's a lot to do. So hopefully what I talk will inspire some of you and maybe work together and contribute towards this. So let me share my slide. Okay, you can see it okay?
Yes.
All right, so one thing we were just talking about weather event and it's being more unpredictable and more impactful these days, especially in the last several years. And then it of course impacts our power grid, right? So this one is from AP, basically Associated Press, and they show that if you look at different state and the number of power outages because of weather, you can clearly see that from 2000 to 2021, which is last year, it has been increasing, and it has been increasing at a really, really fast pace, right? So if you see here, number of outage, and if you see here on the rightmost, there are more and more happening, and this is by quarter. So you'll see almost 10 times for like 40 quarters representing here. And New England is one of the area where it has been increasing more. And then Pacific is another one, and then in South. And the reason for that, because these regions might have more number of weather event that is happening every year, right? So in essence, we are seeing more and more interruption to the power grid, right, with the weather event. What does it mean for the control room? Is some of you already have been there, and we know that every desk has its own job of maybe doing the security analysis, looking at the renewables, and looking at, and what I think that we need a new desk, which is a resiliency desk, and they have to coordinate with, of course, all the other operators and supervisor and engineers. But as these events are unfolding, they have some time before the event hits, because most of these weather events can be predicted in advance with certain accuracy. Not a lot of accuracy, but we can predict with certain accuracy, and we can prepare for it. We can take some proactive action, but we don't have a tools for that. How do we tell operators what to do, right? So we definitely need some tools for that. And these events are very different, right? So there are some wildfire, which is happening in specific areas. There are some snowstorms, there are some hurricanes, and these will have will keep happening in different region. And second is that will impact the grid in a different way, right? Like a flood will impact any low-lying substation, while it may not be impacted as much by like hurricanes and snowstorms. So wildfire will have a different impact. If you put the lines underground, again, snowstorm will have, and hurricanes also will have less impact, but flood might have more, right? Cybersecurity is totally different event, which need to be further think through that. How do we make our grid resilient against that? But cybersecurity brings another dimension because it cannot be predicted in most of the time. So today we'll just, at least I'm going to focus more on weather event. Now, what does it mean for the power grid operators? They will see some alert if the event is going to come. And typically that happens on the TV on one side of this control room. They keep watching the weather. And once the event hit, they will start seeing a lot of alarms. And these alarms need to be taken care in advance, because during these events, these are going to be in hundreds. So no human operator can process and decide that which one to focus, right? So we have to take some proactive action, and then we have to take some kind of tool which will prioritize these alarms and impact and tell them that where to focus on. right? But one thing is sure that these kind of event will put power grid operators in much more stressful condition compared to normal and some failure that is very common in the power grid. And the only way we can help operator to make this decision is through the tools. And these tools need to be very, very advanced, right? So what we can do about it, there's a lot to do. First one is definitely a tool which will tell them expected impact, which will tell them when the event is passing through different alarms and which one to focus on. And after the event has gone, how do we restore the power, right? So these different tools we need, which means that there has to be some planning and proactive action. There has to be some real-time tools during the event, and there has to be some after that, right? And what would enable is only to make a decision, either in long-term or short-term or after the event. We also need to train them to use these tools and consider cognitive science and cognitive abilities of the operators when we do these kind of training to them. And even for the tools, we need to always keep in mind that how much a human mind can process in a short time when these kind of event is happening. And then, of course, we need to provide them a support team before the event and after the event, because during the event, of course, it will be unsafe for the any crew member to do something. But support team in terms of engineering support, in terms of crew support, in terms of repair and all those things, and checking some information, because maybe during the event your SCADA system and your all the cyber system is also down, and may have some sensor has failed. So all these things are needed, but the one that I'm going to focus today is more about advanced tools. So next, I'm going to focus on, like I said, the tools, and then how do we validate it, some case scenario and summary. And I always think that this is a work in progress. So, we are still scratching the surface because it's such a large problem to solve and challenging problem to solve, because even state estimation and all those things is not robust enough to give you solution when your sensor is failing, your grid is failing. So a lot to work on this. So let's talk about tools, and the two tools that I'm going to talk is resiliency planning assessment analysis, which we call it RPA, and the other one is RTR mod, which is real-time resiliency monitoring and operation decision. Now both of these tools, like I said, that's still very preliminary. And even though we have invested several years on this, maybe more than 7 years now, with different funding, and it's still continuing, but a lot to do. And what we want these tools to help us is monitor the resilience, which means that we got to have some metric, and we can see that what is resiliency given a certain event. So this is very important, because resiliency will change if the event is changing, because it will have a different impact on the grid. And then we want to see how it's changing if I do take some action, either in long term or short term. So that's what we want to use that metric for. And we need to compute that metric pretty quick. Quick means like not in milliseconds, but at least in seconds. And continuous monitor the resilience using that tool, right? So that's about situational awareness of resiliency. And once we know that what resiliency will look like if something is happening, and if we take some action in long term or short term, how it will impact, that should enable us to take a decision. So for example, if I take all those alarms that comes during the event and after, we will check that which one alarm need to be taken care first, because if we take care of that, then resiliency will improve, right? So we can compare those things using this index or metrics. Proactive control, corrective control, resource coordination. A lot of these things need to be done, and some does not need to be done in an optimal way because we don't have time for that. We don't have data for that. So we need to apply, some non-optimal way and then apply some optimal way, as depending upon that how much data we have while doing this decision support to operators. And of course, planning and analysis will be very important because, I get these questions very often that one of the utility will say that I have 3 million to invest, what I can do, where to put my storage, where to put my, what action I can take with this limited amount of money so that my resiliency will improve, right? We can answer that question if we know that, if we have the data for the system and we know that what are the possible candidate solutions, we can compare that with the resiliency metric and tell that, okay, this is what will maximize your resilience by investing in this. So different questions that we're asking for decision support is that, what switching action I can take in real time to maximize my resiliency? What kind of storage charging SOC, and if I have multiple, and how do I coordinate my resources so that my resiliency is maximized after the event or before the event? And then sometime, of course, we need to shed load because we cannot pick up all the load because of limited resources. So identifying criticality of load, and maybe even having a multiple hierarchy of top priority and second priority, which we can pick up. Now, most of the time it is also known to utility and community that which one is the top priority, but we do want to know that where to shed and which one to keep. And then, in terms of planning analysis, when we have limited amount of money, where to invest and where to install those things. All of these can be, with the candidate solution, we can use this metric to tell us that what to do. So finally, what we want is that, there is electric grid, either it's distribution system or it's transmission. And then we not only we need electric grid network information with all the resources, but we also need to know that what event we are trying to protect against. We need to know that some spatial information, either it's coming from satellite or it's coming from any other information that we can get for the event. We need to know some vegetation data. We need to know infrastructure data, and which is very important because for grid, everything, all the line, everything is on pole or substation or different devices, which we can call it electrical grid infrastructure. And those data are there, but not in the same database. So we need to pull data from different database. So we have all this information to analyze that what will be impacted. And then of course we need to make a planning decision, an operator decision, and in different scenario. So one is blue sky, which is everything is operating very good. Black sky when these big event happen, and gray sky when event has impacted you. And then we have in recovery mode, which is gray sky. So based on these, what we want to do is that we want to be prepared for expected event. We want to be robust so that event will minimally impact the grid. And then we want to be ready with the response or recovery plan. And these two tools that we are talking about, or we're thinking about, RPA and our RT mod, is going to basically help with those things, right? So before we talk about that, I'm going to talk about AWR, then RPA, and then a little bit about RT mod. It's first one, even though now we know a little bit more and there are multiple definitions that already exist, what is resilience before we put a metric around it? And there are multiple definitions that evolved over time and in last couple of years. I believe that there should be focus on critical load, because if we focus on all the load, then it's reliability, which we already do it. And in simple term, it's the ability of the system to supply its critical load, even in the presence of multiple contingency. Now, if you notice it here, I did say system ability. So which means that it's more like stability and security concept. It's not like reliability, which is a performance-based. Now, we have done, looked at a lot of literature, and we're still looking at as it's coming. The two different approach has been taken is performance-based and system characteristic-based. And I think system characteristic is the one that we need if we want to know that what to do to fix it, because that will be kind of represented in the system metrics, system level metrics. And the one, which I like is from FERC, which is the ability to withstand and reduce the magnitude and duration of disruptive event. Of course, it includes the capacity to anticipate, withstand, adapt, and recover. Now, these three words are important: anticipate, withstand, and recover. And these three things we took and say that, okay, in system, the power grid system, what are the different parameters which will impact my ability to anticipate, ability to withstand, and ability to recover. And then we collect those parameters, we collect those factors, and then integrate them together to form a three different metrics, which we call AWR matrix. So this AWR, A is before the event because it's about anticipate, and it is basically telling me how well is the system prepared for the predicted impact of an incoming event. The one that we did compute is basically driven by CDC public health emergency preparedness and response and weighted sum model. So we basically collected all the different factors which will tell how to anticipate. And as you can imagine, those are the factors about prediction, that how much data we have, what mechanism we have to predict the. So if you have access to satellite data, if you have access to either directly or indirectly or through the tool, then we'll say that, okay, anticipate matrix is going up. And if we have a ability of infrastructure model, then I can also see that how it's going to impact my grid. So again, my resiliency matrix for anticipate part will go up, because those are the factors that I will, take care in my metric for anticipate. The second one is withstand. And this is about how well can system continue to supply critical loads during event. So this one, again, depends on my network, depends on my control, which is the toughest one, because control and predicting that how it will respond is not easy. But network part and resource, where do I have resources? That one is a little bit easier. And if I pre-plan in advance that, either system will stay integrated and system will become, in clustered. So all of those scenario I need to think about and then see that how well we can withstand, which means that minimal damage to the grid. Here, because there's a network and I need to do it, process it quickly. So graph theory based metrics is much needed that for robustness of network. And then for resources, we need to have certain kind of availability of resources so that we know that this will be available when needed and which path it will use to reach to the critical load. Now, remember that we are still talking about radial network, and we are still talking about network to go from resource to specific load. Now, the control part, which I said is more complex, because how the control will respond for this uncertain scenario, the way it unfolds is very challenging. So that's part we are still struggling, that how do we design our control so that withstand capability or metric is higher. And then if it's a switch control or those kind of thing, I think that one is, of course, a little bit easier. But as we get to the control for DER with the polytronics control for all the generation, it becomes more complex. And the third one, so the way we do it, that we collect all these factors, what we can, and those are more than 20. And then we combine that using multi-criteria decision-making process, which in this case, we used AHP, analytical process. And the third one is recover, is something that we have been doing it for a long time. In most of the time when we have a fault happening and the system gets damaged, we try to recover, and we have been doing it for a long time with the help of OMS, which is outage management system. If the outage is large scale, such as this caused by these weather event, it will be slightly different to figure out that where the outage is, but that is something that we have been doing it for long. But we have not given that as a metrics and use that for resilience metrics. So here also, if you think about recover, it will depend on that how many ways I can reach to my critical load. And so that means network, control, and resources. So here also we apply some selected graph theory based metrics. And then again, resource and availability of those, and then multi-criteria decision-making process applied with the AHP to get to the recover metrics. So in short, this is how we integrate all the different factors for AWR. And here are some factors are shown. For example, anticipate domain, we divided into threat and vulnerabilities, power delivery and loads, and restoration and recovery. And then we try to get those things for anticipate, critical load, not lost, generation availability, critical load demand. Then topological resilience is the one which is based on my graph theory metrics, where we want not single node to take all the path. So you can imagine that I can go from 3 resources to the 2 critical load, but all the path is using one node predominantly. And I can easily get that which node is that predominant, and my metrics should go lower, because it depends largely on one, even though there are 10 paths possible, but it depends largely on only one node. So based on those things, we can easily compute, centrality and betweenness centrality kind of indexes from graph theory, and then get those factors. There are several different factors that can be compute from graph theory. And then for recover metric, again, path redundancy, generation redundancy, switching operation, all those are important. This is not a complete list of, but some key one that we use. Finally, what we get out of this is resilience-based planning and investment, and then also monitoring the operational resilience, and then decision support for proactive control and corrective control. So next one is RPA, which is our resiliency planning and investment analysis tool. And as you see here, there are some small fonts, but what we want is system information. So we want this tool to be connected with your DMS or ADMS if you have in the Power Grid. So all the information will basically flow from there to here, or even OMS. We can get this information, which is GIS map, and which is your grid infrastructure, and then weather mapping onto that. And different tab, as you see here, is showing the system information, then threat modeling analysis, and then predicted asset damage, and then how do we manage asset and crew in planning, and do we need to get more assets or for redundancy, or we need to get more crew member to prepare for something. So this can answer, because we can compare the metrics again. And then resilience analysis, which is going to compare 2 different scenarios or multiple scenarios as we ask for, and then resilience investment analysis. And each of these tab opens up into more information for infrastructure, network details, generating unit load, and resource information. It will become more complex once we start doing for transmission. So far, we have done for distribution, although for transmission, we have done a lot of set of algorithms, not the tool. So, and all these tools, we used open source, to develop all of these. So It looks at multiple database that comes and we worked with a couple of utility members or partners to collect the data and basically show them this kind of information. It would got to have some user interface, middleware interface, and data abstraction layer. And the other one is RT/RMARD, which is the real-time resiliency monitoring and operational resilience support. And here you see we have system information and then resilience monitoring. And then it is alarm and service area outages. Basically, we want to process those. And then decision support, which is the most important one. And each of these tabs again open up to several sub-tab where we can get the information. Especially the left bottom one is showing you resiliency metric for these 5 different colors. And we can compare that for anticipate, withstand, and recover. So here is example where we are trying to compare resiliency score. If we plan for it and charge our battery in advance, compared to we let it operate as a, we call it 2 different mode, economic mode and resilient mode. So you can compare the economic mode and resilient mode and see that how the, what to do for resilient mode. Right now, we don't have that mode, right? So battery will keep operating as it is, right? But again, this is just one example. Same logic can be applied to like pump hydro storage or any other storage technology too. So then next comes the decision support using these tools. And that's where a lot of work need to be done, right? So here are some examples, like for pre-event proactive control or post-event corrective control, we have multiple things to do. And some example is that first we need to know that damage and outage estimation, right? So how do we use satellite images? How do we use ground camera and weather prediction to find out the damage and outage estimation with the minimal time, right? Because that's what is important. And then if needed for proactive, do we need to make a segmentation of our grid so that the part where the damage is expected to happen will not cascade to the rest of the network? So how do we decide that part, right? And that's a good problem to solve. Then in terms of distribution automation, where we have a lot of flexibility, how do we use it to make a sectionalization or make a section or cluster in a distribution grid so that we can, again, any disturbance does not propagate. And second one is if we have enough number of DER, then how do we isolate that part? Sometimes we might need to find a temporary microgrid, because with the microgrid, we still know that the power that we get, and especially if it is one of the diesel or it's not, or even steam or gas, it is not most economic. So we want that to be only isolated during these kind of event, but most of the time it will be connected with the grid, right? So that's how the most of the microgrid work anyway. And what temporary microgrid is that where we don't have a predefined boundary of the microgrid, and we keep changing it as needed in different, because we cannot make it totally dynamic. Otherwise our protection and everything need to be adjusted, control need to be adjusted. So it's more about possible settings that we can apply for microgrid and which can change between different possible boundaries. Why we will do that? Because to maximize matching of DERs with critical load, and which is dynamic, right? Because which one will be damaged, which is available, we don't know it till the event happens. And sometime we might have a small generator installed on the truck and move it to a different part to power a critical load. This is something that we already do, which is a backup power to support individual critical facilities. Post-event, we can do the same thing, have some mobile generator which can be moved around. Army does all the time. Then restoration using sensor information, trouble call. So all the data that we can get, it's more about outage management, but with not in reliability in mind, but resiliency in mind. And then, of course, how to use the control automation and DR coordination after the switching is done. And then microgrid with changing boundary that will be needed in corrective control too, not only proactive. And then network microgrid with distributed optimal control. So this one is more robust, being distributed. And distributed, and I'll talk a little bit more about that, is inherently more resilient control. And then queue and logistic deployment in support of recovery is all things that we need from these tools. Now, again, these are only few examples. There are more things as possible for doing that. And each of these can be multiple algorithms that need to be developed for these. Let me a little bit talk about distributed control. So in distributed optimization and control, which does not need to be optimal, even agent-based control, which is non-optimal, will work for distributed control. But if we can optimize it, that will be even better, right? Because we can put resiliency goal or resiliency metric maximization into these small agent or a small controller to maximize our resiliency with the different goals. So there are multiple ways to do that. One is decomposing the problem, where you basically take the constraint and equality, inequality constraint, all those, and an objective function locally, and then coordinate, exchange variable between them to coordinate. The second one is like a feedback control. And again, this is very higher level, broader classification. There are more sub-classification possible. We do have a recent one paper on this, which talks about all the different things that can happen. Now, why it is inherently resilient? Because if we distribute the problem into different agent and controller, then even if one fails, the rest of the controller will keep working. So redundancy level, which used to be centralized and backup controller, now is almost, if there are n number of components, then you have redundancy of n-2. Basically all can fail except one, right? So except two, which can coordinate. So redundancy has increased a lot, and that's why it's inherently much more resilient. Now, once we start doing distributed, there are a lot of problem and challenges to solve. First one is that how do we guarantee optimization? How do we distribute the problem? And then how do we set the parameters because there are a lot of new parameters that need to be set up when we start exchanging variables between these, how much to exchange. And if you are doing feedback, then again, the same, how to set the parameters. So now let me talk about validating it, and this will be a very short section. We do need something like a substation environment with a real sensor and controller. And then we need something like a control center environment. Of course, these are very small scale that we have set up in our lab, but these two are definitely needed if I want to put our tools out and push it to a real utility. So we have to do preliminary testing here, and then in large scale testing with the utility, and then solve the problem. So in a little bit more detail on this, because we can even integrate our substation environment and control center environment together. So this is based on one of the projects that we have been doing with NSF Big Ideas, and the partner is Berkeley and Vanderbilt in that. And here we are also collaborating with a company called Resilient Grid, which makes visualization software tool considering the human cognitive science and cognitive engineering to develop these HMI. And we are working with the INCSys Power Simulator, which provides us basically their all the EMS function, like contingency analysis, alarm, AGC. So all those are there in that engine. And we are bringing this set of data from our substation environment to a common database. And we also have a detailed cyber network model so that we can simulate those. And then finally, we're using PingThing for synchrophasor data set database and managing it. So all these integration is challenging, but we have been making some progress on that, and so we can use our tools in this real-time environment. And then cyber physical simulation test bed, which is kind of imitating the substation environment with the real devices. We mainly have SEL, but GE, ABB, and several others. And we worked with ARPA-E and Vanderbilt to develop this REAPS node, which is for distributed control. So the small controller that you see in the down figure, the three, those are basically representing a distributed control. Of course, it could be more, it could be hundreds. But we just demonstrated with these three that if you have a system, we can put substation devices in terms of, here it's only PMU based control. So it takes the PMU data and then goes to the bigger board. That's where distributed optimization is running. And then we get the actuator and then we implement that control. So we were able to demonstrate that it works, even it was suboptimal. And some of the cases that I'll demonstrate now, like I said before, that what we are doing is only a fraction of things that need to be done, right? For transmission, for distribution. So there are different tools which is being used for different systems and different event. So I'll pick a few examples. For example, we worked with Alaska where the tsunami was a problem, or at least expected sometime. And what we did is that we analyzed in terms of assets, even though you can also plan with the crew members, in terms of assets, where to invest our money in such a way that resilience is maximized, right? So here they wanted to buy a battery and see that how it is going to maximize my resiliency. So we can, again, using the same metrics, I can compare. You can see case 1 and case 2, which are two different cases of batteries. And then it shows with battery and without battery, how much advantage you're going to get. So with the resiliency advantage and the amount of money that we're going to put for two different options of battery, and you can have a multiple, like 100 of options by placing it different location, compared, and then decide that, okay, where to put my money. Second case, I am going to talk about resiliency decision support. And this one is proactive control. So before the event is going to happen. And the whole concept here is based on the fact that you have switches in the field, which is automated. And then you have a switches in the field, which is manual, right? So you have a three different kind. One is automated, one is remotely operated, and one is manually operated. Now, automated, if it's there, we don't need to do much because you already set the logic for that. If it's a manually operated, crew member has to go and open it or close it, well ahead of expected event, so that they are safe. If it's remotely operated, then you just need to operate it, and you need to know that which one to operate. So we have the minimal impact on the grid. Now in this one, what we are looking at is that how do I make a clustering or make a cluster of system in such a way that the impact is not propagated. So we isolate the part which is going to be impacted anyway. And if we isolate it before the event is happened, if we have a good confidence on the prediction, then it will definitely will not propagate, because that part is already isolated. So something which is going to be isolated anyway, with a bigger part, we are taking a proactive control to isolate the minimal possible part. And that way we will have a continuity of power, because that's reconfigured in advance to those part which will be isolated if we do not do anything. But now we isolated in advance, and connect it to another part so that the power can be continued. And now it's a two-step problem, two-stage problem, because one, we need to decide the manual switching, and one, we need to decide about the automated switching. So again, the focus here is that if we have a good prediction, then all the component which is going to be de-energized because of the impact of the event, how do we de-energize at once of the event so that the disturbance does not propagate? And it will require us to send the crew. It will require us to look at a lot of database and then get the data from the ADMS so that we can put resiliency management system, which is basically RTR MART here, to compute the metrics and decide where to isolate. So this one is the Alaska system that we worked with in CEC, Cardova Electric Company. And of course, we did use aggregated model, but it can be done for IEEE receiver system or even any larger system. And this is how it will look like after the modeling. So we have a predicted event and it's progressing well. And then there's a distribution network, which is a lot of interface of sensors, and we are getting those data. Early warning tell us that, okay, this is going to hit at 1 hour or 2 hours later. And now we need to send the crew so we can open the manual switches. And then, just before, few minutes before the event is going to hit, with the uncertainty, which we already know, we open the remotely operated switches, and automatic switch is going to take care of itself. Or sometime we need to block them that don't open automated switches, right? So all this action need to be taken. So this is very complex and very busy slide, but I isolated it so that I can talk about two different stages. I will not go into a lot of detail, but the whole concept is that knowing about your economic mode, knowing about your resilient mode, and as soon as event is predicted, you change your mode to economic to resilient, and then you compute a couple of requirements for your resources and requirement for your network based on this, so that we isolate the minimal part and do not allow disturbance to propagate. And sometime we will have a lead time sufficient enough to send the crew to open the manual switch. Sometime we do not. So based on that, we can change our algorithm. Stage one is isolation of network with the manual switch, and then stage two is the automated switch. So stage two is safety constraint switching without isolating part which is important for us. And all of these two going to basically two places. So one is situational awareness and one is decision support. So you see that 2 DS is decision support and 2 SA is situational awareness. And some are going and some are coming back, some are going to 2-fro. But all of these can be formulated and put in set of equation to with the objective function and constraint, considering all the power system constraint, and then we can solve it. And you can also solve the same thing with the distributed approach, which is still in progress that we are working on. But here's the result that you see. And again, this is only one example of different things that need to be done and different things that we are doing. Is if I take action in advance, then overall resiliency after the event. So you see that blue curve, which is showing the resiliency after, is higher after event is gone. Right? If you don't do something, then it will become red one, which means that after the event, it is not recovering and the resiliency is down. Right? And there are different scenarios that is shown here in the red, blue, and green. Now we can and a lot of work need to be done for this prediction, right? So this example is showing that there's so much more possibilities. So here it's about against wildfire. The other earlier one was in Alaska with tsunami and snowstorm. A lot of different things need to be done. So you have to forecast the resources, we have to forecast the event, we have to forecast the damage impact. We have to put some tools so we detect as soon as the anomaly is happening during the event. And then we have to generate the alarm and we have to classify it. Then we also have to detect the event and classify that what kind it is. If it's an outage event, then we need to focus more on that, and then rank them in such a way that operator can make a decision that where to focus, and then find out that why it is happening, what was the root cause that caused that outage, and then provide decision support. So the whole process is a little bit longer, which of course I did not talk about today. We only talked about monitoring and decision support, but this whole process need to be followed, and each of these is a very challenging problem to solve, while you have less access to data and you have less access to your system information. This one is reinforcement learning based decision support against wildfire, which we are working with the University of Houston, and it shows how we can get the data and do the optimization through reinforcement learning to find out that which part for resources and network need to be modified to minimize the impact. So basically the control action is switching, and as the wildfire is propagating through your system. So I'm not going to detail of these in interest of time, but there are more possibilities. That one thing that I think is we need Alexa for the power grid, or Siri for the power grid, because when the time is stressful for the power grid operator, we want to make it easier, but only if we have confidence that what were the data they're asking, we will get it very quickly. So we have this tool called Dingo, which is digital assistant for grid operators, NLP based. And again, it's very preliminary. We have, but we did the proof of concept with implementing it, and showed that in during the different event, how we can use this kind of virtual assistant to help the operators for faster action. Well, so there's a lot to talk about because each of these is a challenging problem and to solve. But just to summarize, extreme weather events are increasing and expected to increase as we know with the climate change. Right now, we don't have a tool which is focused on resiliency, and especially against extreme impact of these tools. We do training, we do some drills against like wildfire. We kind of do that, but those trainings are are using the same tool, which is not designed for resiliency, which is not designed for extreme events. During extreme events, those tools probably will not even converge. It's not robust enough. And situational awareness is, of course, very important for grid operator. Synergy is important between the operators because we need to understand how human mind works in stress and how human mind will work if it's very bored, right? So more tools needed. I think RPI and RT mod is just a start. A lot of work need to be done, especially to enable each of those algorithms to make them support a different decision-making process. And we all know that all these optimization function that we have and all the physics-driven tools that we have, if data is missing, if the data is not correct, it's not going to converge. It's not going to give a solution. So we do need some backup. And that's where the machine learning and analytics comes. And all of these can be used, which I did not talk a lot in detail about, anomaly detection and classification, event classification, localization, and even decision-making like reinforcement learning. But there's a lot of scope in that area. And unless we get confidence in that, I think it still should be backup, not the primary tool to take action. depending upon what application we are talking about. So it need to be applied very carefully to the problem that we are trying to solve. If our physics-based is happening, those are explainable. Those we can take it further down to find out and find the root cause so that we can take action. While in machine learning, that's not the case yet. So we only need to apply when we cannot solve it using our conventional optimization method or conventional method, physics-driven that we already have. Validation is very important as we try to develop these tools and with the real operators and with the different scenario which are more practical. And using the data, even though we can simulate those set of data, there's a real big difference with real relay, real PMUs and in the lab, because all the noise that comes with that, we cannot really try to model and imitate exactly the same thing. The last thing is the way human mind work and under stress. And knowing their cognitive science ability is very, very important, especially for enabling them to take a decision during this team event. With that, I would like to, of course, thank all my students and the collaborators and postdoc, which really did all this work that I presented today, and funding agency to support it. And thanks so much, Maria and Dan for inviting me here and organizing this seminar series.
Thank you very much, Anurag. Really a lot of thought-provoking ideas and questions, a lot of things to do. We have a few questions. We don't have to stick to exactly 1 hour. If people want to drop, that's fine, but I think we'll go through the questions. Maybe Brian Patterson, maybe you want to ask first?
Sure. I think actually it was covered. And first of all, great presentation.
Yes.
It was very informative. I was asking, to what extent could semi-autonomous distributed intelligent control help minimize the stress on central hierarchical control? As you mentioned, the human intervention at the higher levels gets more and more complex. So if you can go to distributed control as far down into the system as possible, then all the decisions are really just acting on local conditions, and they're more easily sensed, I think, at that level. And the decision-making alternatives are somewhat simplified. Is that true, or am I missing something? I think you said that distributed control is probably one of the better overall solutions to resiliency.
Yes, yeah, I think distributed control will be much more resilient because redundancy is very higher. But at the same time, we need to make sure that because those distributed control will be subject to the same kind of more open cyber attack compared to centralized. So centralized, we can put all our effort to secure certain computing devices. And while in distributed, the effort will be much more needed. So if we do go on distributed way, which is, I think it will be only way as the scale of the system and resources are increasing, that will be only way. But we need to, in the process when we do that, we need to have this emergency kind of button, which will change from centralized to distributed control, because centralized we cannot process it, and we don't have enough information and data to even run and make those tools work. So, but eventually, it will, I think in next 2 decades, 3 decades, maybe we have to slowly make a transition to distributed.
I would like to add one comment because we've been working now, first at CMU, and now I'm continuing that work at MIT. It really is not just either distributed or centralized. It should be interactive. It's the information exchange between different levels of aggregation and clustering you were talking about. So those clusters even evolve as a function of operating conditions ultimately. And if you want making it more autonomous, but the role of aggregation in particular is going to be cybersecure aggregation. And some of you may be familiar, I've been advocating these, what we call DIMOS, dynamic monitoring decision systems, right? So there is definitely interactive mode there between the different levels of coordination and at least aggregated users or large industrial commercial users.
Yeah, I didn't mean to.
I want to draw attention to people's I led the study for Puerto Rico with Lincoln Lab, in which we show potential of that. It's quite a bit, because even if you lose a lot of equipment, you have these distributed islands and pockets left, and they have to coordinate themselves and in the distributed interactive way. And you can save very large portion of and serve the critical load, which is, as you said, Anurag, is the basic definition of resiliency. That way, while if you just apply, I had the question myself here, if you apply existing tools, but I think you answered that question, Anurag, most of them will fail, yes. Will not converge. So I think the open question there, which I don't think many people are paying attention to, is how do you align the policy and incentives with the minimal information structure for information exchange, which is cyber secure and so forth. And I think people just take their own approaches. It's either centralized or stakeholders say we don't have to do anything. There is a lot of work to connect this interactive process, and because there's lots to gain. So that was my comment. I don't know if you want to add something, Anurag.
No, I totally agree with that. And that's why I was trying to emphasize that there is a lot to do in this area, as we will see more and more often that centralized tool will fail, and especially with cybersecurity in mind, it will be more challenging.
Yeah, but it's very interesting what we showed in this Lincoln Lab study. You run even ACOPF to finding how to maximize the serving the critical load, and it's going to tell you whom to ask for help, right? Because there are these coefficients which give the most critical constraints. And so I think there is a huge, I remember Anjan Bose mentioning this in some recent brainstorming. We really need to rethink the software for this, and what information gets exchanged and what level of software and functionalities we need to have. It's not going to be just using the business as usual software from control centers.
Yes, yeah, because those were written long back, and I think the improvement that has been done in that, even for N-1 security or higher security aspect, and then robustness is not there.
One question that I threw during the presentation was, and I think we have literally no software tool for that. Like even when you want to do investment planning for distribution, like where to enforce to add storage, for example, and things like that. How do we weigh the severity of the outcome versus probability of happening? Who takes responsibility for these are low probability, high impact events potentially. Are there any thoughts you can share on that?
Yeah, so experience that we have working with Idaho Falls utility and then Alaska, we really gave them some answer to them, and I think the tools for those events when the system is blue sky or even a gray sky, that they do have some tools to do that, right, which will give you some solution. And if we use that one and then we use this resiliency matrix driven, and if the answer comes reasonable, so we are not going to optimize it, and that's why I said that a lot of time optimization might not happen, because the tools to take care of other constraints like a space constraint, take care of data constraint, because if I'm going to put a battery at one location, it cannot be just anywhere. So if I have 100 different nodes or substation in the system that I can put, a lot of those are constrained because I don't have access to data. I don't have access to extra. And if I put new cyber network to bring the data from there, maybe it will cost me more. So all the option becomes narrow anyway. And then we only have a few options, like 6 options, 7 options to work with. And if I can run my, this RTPI, which is resiliency metrics, and then I can run the some economic mode kind of, a lot of tools that exist from NREL and Sandia, and then find out of the 7, which one is maximizing my reliability versus resiliency and the practical constraint, then we should be good on that.
Can you also clarify, at one point you were talking about performance-based approach versus system-level approach. What did you mean exactly by that?
Yeah, so, right now, reliability is a performance-based approach, because we look at, loss of load probability and all those kind of things. And then we finally say that, okay, how many minutes of power we lost in this year? We don't look at that how and why it happened.
Okay.
Right? So we don't take the system model. We just take the data and compute it. So that's a performance-based metrics. While in stability and security, we don't look at performance. We look at the system model. So basically model-driven. Yeah. So model-driven is system. And I think resiliency should be model-driven, because I need explanation that why resiliency is going down and what I can do to fix that.
That is great. I understand now. I don't see any other questions. Are there any ad hoc quick questions here by the audience?
I have one additional if nobody else does.
Please, Brian, yeah.
In the performance data that you showed, I think it was your first slide actually, was there a minimum threshold for recording in the data an impact, a disturbance impact? And because my understanding is that, generally speaking, that utilities are only required to report disruptions that are above a certain criteria. So if you actually took the impact of every disturbance, even down to a single feeder line or home or whatever, you would get a much larger data base to work from. Is that true? Or?
That's true. Yeah. So for reliability, they only look at the outage that is reported by a homeowner, and that has to be widespread. So in terms of size of outage that they look at, is already multiple homes, right? And we're still talking about reliability. And then it has to be outage more than certain seconds and sometime in minutes, depending upon the policy that a different state has developed. We count them and we ignore that if it's only for a few second outage. So we don't count that. And if these event is caused by a weather event, if I remember correctly, that the policy that we had in the past says that don't count that either for reliability computation, because this was out of your hand. So and that happens like once in 3 years, once in 4 years. So you don't need to count that. So when they report the reliability number, they take out extreme event out of that. But that one need to be considered for resiliency.
Yeah, I was going to just report having a long time ago in my career operated a factory that did semiconductor clean room work. And that when we had even the small power failure, even as a result of mechanical switching errors and things like that, we would sometimes have multi-million-dollar losses, which were very hard to recover from, even though they were very isolated. And I'm wondering if the value of resiliency is highly underrated because of the way things are reported at this point. And I totally understand why there are rules about minimum thresholds, but from a planning future viewpoint, it's that data that's under the shadow right now that probably is the most useful for people to understand, because it's the ones that have the most direct impact to them.
Yeah, no, you're absolutely right. I think not only that, but there's no market, or there's no algorithm that we have which will say that what is the resilience value of certain resources or changes in network that we do. I know that PJM is the only one which integrated resilience into their transmission planning, and that'll be the way to go. That at least in planning, integrate in the planning first, and then over the time integrate in operation. But we definitely need more policy and more regulation, which will put resilience value to assets.
So one comment on policy, because at MIT they do a lot of policy. It is a sort of course level approach to policy. It never gets down to, end to end, right? In other words, it's all capacity based or type of resource generation, more source of generation for environmental. So I don't know how much effort is there at IEEE. You are very involved, Anurag, but I think that those dots need to be connected also. In other words, how detailed policy you need for what purpose. And I think when those questions come up, everybody points out to NERC, and NERC is just doing bulk power system. And so the question is really, you probably know, I'm very curious, I don't know the answer to this. For a while, people were talking in the US in particular about doing DERMS and ADMS and stuff like that. In other words, control centers at the distribution level or microgrid level. It seems like that has a little slowed down or not much is happening. What is the story there?
Yeah, because the microgrid still is not economical. And the second,
Brian is going to violently disagree now, but anyway.
Yeah. So it's driven by we talk about resilience value and reliability value to customer, and it's driven by them. So the one at least in the US, I would say that it's mainly driven by the customers to install the microgrid. It's not driven by utility or government. While in other countries, I know that a lot of other countries, government is putting more money into microgrid because there is no resilience value assessed right now. But if we add it, then microgrid will be attractive, right? So government and utility, once they start looking into microgrid being economic and microgrid being more integrated, of course our system will become more resilient because more number of load will have access to power in control mode. But once we get there, till we get there, and again, it's the way our utility is structured, mainly investor-owned utilities. And in that case, they will always go for something which is more economical. Some are adopting, they're collaborating and supporting microgrid efforts. But if I look at last 100 microgrid, which I look in as a microgrid symposium, that happens. All the example that I look at, it's mainly driven by customers, not by utility and government in US.
So is it fair to say that all the distribution stuff is right now at the US, I'm talking, Europe is a little different, sort of pre-programmed, and it's not online, data-driven? I'm talking about distribution, I'm not talking about microgrids.
Mm-hmm. Yeah, so we always had less visibility and less data from distribution grid. And only a big change that happened was with the smart grid grants, which it becomes, access to more and more sensor data, and the smart meter investment. Again, both are driven by government, right? Basically, investment that we got, we had a big jump in distribution system data and visibility. But there's a long way to go to make it even ready for distributed, and the protection will be the biggest thing that need to be solved for that.
I want to mention something about protection. When we were at CMU, Yi Zhang, one of our PhD students with my colleague in communication, she did early on, this was at university, you do things sort of ahead of time, support vector machines for protection. Mm-hmm. Those are easy to implement. And I remember talking with Damir Novosel. I said, Damir, why don't you put, this is quanta technology, they are doing tech transfer. I said, why don't we do that? He said, well, I did 20 years ago, my PhD thesis was in the same direction. And so even protection really rings the bell because, it is probably the easiest way that we have on the distribution systems in particular to make them a little smarter, you know, that they learn locally and they self-adjust. I don't know how much work is on that, but there has been R&D work which shows with very high probability you can train them. And you don't have to train them for extreme events. You train them during many conditions as conditions change. And they are not impedance-based anymore or something like that. They are much more adaptive. That's where I think that's one of the first examples of distributed machine learning that exists. As I said, if I understood Damir correctly, he did his PhD thesis who knows when on that. And it's now we have to revisit all that work, I think, rather than just, if we restart from scratch, but memory in R&D and the knowledge and tech transfer is really slow. So then we restart and it's going to take another 20 years to even learn what we can do again. And so when are we going to build these things? I'm getting a little impatient here. So it's up to you guys to I think I know you're playing very leading role, and maybe you want to mention that the reason that Anurag and I cross paths quite a bit, we are co-chairing these working groups. So you may want to invite people. Some people have dropped, but maybe you want to give the information for the IEEE some general meeting if people want to contribute and sign up.
Yeah. I think.
What is the official number working group on resiliency, right?
Yeah, so I mean, in SIGRE we have number, but in IEEE we just call it working group for tools.
Sorry, is it task force or working group? It's working group now.
It's still task force. So
task force. So if you look into program for IEEE for general meeting, you know, this year, please come, because I think that this area needs a lot of help and input. And Anurag and I have a panel, you know, different people will be speaking, but as you pointed out many times, Anurag, there's really a lot of work to be done. And used to be that we did those things because we were interested, but now it's needed. So
Maria, if I may comment on the resiliency valuation issue. Today, unfortunately, the way our regulatory apparatus is configured, it doesn't give a weighting factor for resiliency. Possibly, among other reasons, that resiliency is a very much differentiated value, depending upon what kind of a customer are you, where you are, and so on and so forth, and you know how you value resiliency in whatever you're doing, whether you're a residence or a business or what have you. What's happening is that microgrids are being put behind the meter, so to speak, sort of in a funny way, ripping the opportunity away from utilities to become more of a service-oriented institution, because they're not generally allowed to differentiate rates based on resiliency. They're based on what you would call common commodity kilowatt hours and so on. So until that changes, the utilities are put at a tremendous disadvantage in terms of competing on a level playing field with those people who are deciding on what resiliency value it means to them behind the meter, and taking the microgrid action at that level. So microgrids, you had made the comment that microgrids aren't economic yet. For many people, they're way past that level where economics are the only reason they're putting in microgrids, because they realize the value of resiliency to them. And the actually even kilowatt rates are getting closer and closer, you know, depending on how you look.
So my comment was more about customer oriented, right? So that's what it is right now. For it.
So there are, yeah, I was going to say there are some utilities now that are seriously investigating this whole issue. And some of them, one that down in Florida has actually put in some pilot operations where they're dealing with networked, you know, microgrids and nanogrids at a community and neighborhood level. They were forced to do it under a common rate, unfortunately, but they're willing to invest that opportunity now, if for no other reason, to understand the customer's perception of resiliency and how that might play into eventual rate determinations.
I think that Puerto Rico also, this is because of geography, in particular the middle mountainous part of Puerto Rico. You know, you cannot it's much better to put it in the distributed way and where the customers are, rather than drawing long lines between faraway customers. And so there is an effort. I think national labs are doing quite a bit of research on, given where the load distribution is, where should you place the microgrids? I know Sandia did a nice project on that. But I'm asking, okay, we did the study, how do we move the next step? So I think on that note, I think this was a very serious subject, Anurag, and I really appreciate your time and all the work that you are doing. So let's stop here. And if people have follow-up questions, here is Anurag's email. And thank you very much to everybody.
Thank you. Yeah.
Bye-bye.
Great presentation. Thank you.
Yes.
Thanks.